It is my pleasure to welcome you to the sixth part of the crash course Foundations of Quantitative Research. This lecture is about descriptive statistics. I would like to explain the purpose of descriptive statistics in academic research papers, the scale of measurement, and then we're going into the descriptive statistics, the frequencies, the measures of central tendency in distributions, and then the measures of dispersion. First, the purpose of descriptive statistics. Descriptive statistics, it's in the name, describe a sample or population by summarizing a data set through coefficients. Here you see an example. This is from the paper, The Relationship Between Organizational Commitment, Commitment to Supervisor, and Servant Leadership. My co-authors and I used descriptive statistics to describe how many women, men, and non-binary people were in our sample, so that the reader knows from whom did the data come. Furthermore, we described, just to give the reader an understanding on what level our measured constructs were, we described our measured constructs. For organizational commitment, the 4 facets, same for commitment to supervisor, and then for the facets of servant leadership. We reported the minimum value, the maximum value, the arithmetic mean, and the standard deviation. It is very important to note that only with very few exceptions, you cannot write an academic research paper that is solely based on descriptive statistics. Descriptive statistics have nearly always only the purpose to describe the sample through socio-demographic and context variables. You virtually always need inferential statistics for academic research. These inferential statistics I will explain in the last part of this crash course. Now, scales of measurement. And the beauty in quantitative research and statistics is, if you understand one step, the next step will be much easier to understand. And the precondition to understand descriptive statistics is to understand the scales of measurement. You can distinguish between categorical scales of measurement and metric scales of measurement. Common language, or to put it in common language, categorical is everything you can put into drawers or boxes, to categories. And metric is everything you can put a number on. So within the categorical scales of measurement, you have a nominal scale of measurement. Here you can only say values are equal or not. I think the best example is gender. We cannot say a man is more than a woman or woman is more than a man. We only can say men and woman, that's different, and put them into different boxes, into the men box, into the woman box. They're different, but we cannot say one is more than the other. To say one is more than the other, or higher or smaller, then we need an ordinal scale of measurement. So here we can say values are equal or not equal, and we can say they're larger or smaller. Best example that I can think of is Olympic ranks. We can clearly say the gold medalist is better than the silver medalist, and he in turn was better than the bronze medalist. But we cannot say how much better the gold medalist was in comparison to the silver medalist. Just think of 100-meter sprint, Olympic Games. If there's just a tenth of a second between gold and silver, you cannot say gold is double as good as silver or something like this. You can only say more or less. If you have a metric scale of measurement, then you can say how much more and how much smaller the values are in comparison to each other. Normally, it's only important to know I have a metric scale of measurement in the context of social sciences and academic research in this realm. But you might distinguish between interval scales and ratio scales. The difference is that with interval scales, you have an arbitrary 0 point, whilst with ratio scales, you have an absolute 0. For interval scales, think of temperature. Kelvin and centigrade, they have a different 0. A ratio scale is like height. If I'm 0 inches tall, I'm not existent. Money is another example. If my income is 0, I don't have any income. And here, using income as an example, you can also say how much more and what the relationship, what the ratio is. If I have an income of £100 and you have an income of £200, you have double my income. So it's always lovely to have a metric scale, as you will see in a moment, you can do most with it with regard to statistical analysis. Let me give you a few more examples that you might find in questionnaires. Nominal scale. I already used this example, gender. What gender describes you best? And you tick female, male, non-binary. An ordinal scale of measurement, an example would be, please evaluate the following products by bringing them into an order from 1 best product to 3 worst product. Metric scale. How old are you in years? 20 years, 30 years, 40 years, whatever your age is. Important for academic research is a question type, and that is the rating scale. Social sciences, you find different forms of rating scales at the heart of virtually every project, which has to do with questionnaires. A rating scale, you can see an example here. How satisfied are you with product XY on a scale from 1 completely dissatisfied to 6 completely satisfied? Then participant has to tick from completely dissatisfied, that represents 1, 2, 3, 4, 5 to 6 completely satisfied. Strictly speaking, this is an ordinal scale. However, you can treat this as a metric scale and use then all the statistical procedures and analysis that require a metric scale of measurement. Let's go to frequencies. Frequencies you can use with any scale of measurement. Normally it's used with a nominal or categorical scale of measurement. You have absolute frequencies. That is just the number of times a value of a variable occurred. For instance, here we have age brackets 20 to 29, 30 to 39, 40 to 49, 50 to 59. And this example, 200 participants were in the first age bracket 20 to 29, 233 in the next age bracket 30 to 39, and so forth. Normally, you do not report absolute frequencies in a research paper. What you want to have is relative frequencies. There are exceptions if you're on a very fundamental level with your research regarding experiments and so on. Then absolute frequencies might be the right thing to report. But normally, so there's normal survey, cross-sectional designs, you normally always report relative frequencies. Relative frequencies, you can also say, it's just percentages. It is the ratio of an absolute frequency of a value to the total number of values for a variable or observations. And for the same data set, here is the relative frequencies on the right-hand side. So that means, in our case, 22.45% of the participants were in the age bracket of 20 to 29, or 26.15% of the participants were in the age bracket of 30 to 39. Furthermore, you can combine two variables, then you have cross-tabulation. It's just combining two variables and report the frequencies. On the left-hand side is an example. Again, our age brackets 20, 29, 30, 39, 40 to 49, 50 to 59. And then we combined our age brackets with gender. Here just female, male to keep it simple. Now we can say 22.08% of all female participants are in the age bracket 20 to 29. 28.35% of all female participants are in the bracket of 30 to 39, and so forth. The same, of course, for the male participants. Of them, 22.84% are in the age of 20 to 29, 23.78% are of the age of 30 to 39. Let's come to the measures of central tendencies, and also I would like to deal with distributions here. You have three main measures of central tendency: the arithmetic mean, the median, and the mode. The arithmetic mean is simply the sum of all values divided by the number of observations, or the number of values. Here you need metric scale of measurement. That will not work with an ordinal or nominal scale. The median is the value that separates the higher and lower half of a distribution. You can use the median for a metric scale of measurement, but also for an ordinal scale of measurement. Finally, the mode. This is just the most frequent value of a distribution. And here, the scale of measurement doesn't matter. You can use this with any scale, but normally you would use it with a nominal scale. And I believe the mode is the least important measure of central tendency in academic research. At least I cannot remember any report, and definitely not any project I was involved in which the mode was of any relevance. But there might be one out there. To explain these measures of central tendency or simplify them, I have a simplified data set here, assuming we have 9 participants. Let's assume the variable A is the age. So we have one that's 23 years old, then 27 years old, and so forth, to the 9th participant who's 75 years old. The arithmetic mean, we sum this all up. This will be 405 divided by 9 gives us an average age of 45 years. The median, the value that separates the higher and the lower half, in our case, it is 40. Then we can say roughly half of our participants, or 50%, are 40 years of age or younger. Roughly half of our participants, or again 50%, are older than 40 years. The mode with these numbers is 60, as there were 2 participants who stated there is 60 years of age. Let's have a look at distributions. I know you can say you don't want to have, or just want to say what you want to have, but you don't necessarily need to have. So what is sort of the ideal distribution, the most beautiful one? That is the normal distribution. And that is such a bell-shaped distribution that you see on the right-hand side. In these cases, the arithmetic mean and the median have roughly the same value. But you find a perfect normal distribution, you probably will never find. And an imperfect normal distribution, it's also very rare to find. Normally, you have skewed distributions. And in the middle, you find a right-skewed distribution. That means you have lots of participants that have rather small values, and then you have a few participants that have rather high values. You can think of this as an example. You should companies or company size. We're always, or quite often, we're thinking of the large corporations, British Airways, HSBC, and so forth. But there are actually many, many small companies. Think of your local, the next pub, the corner shop, restaurant. We have lots of small companies in our economy. And in these cases, or these would show such a distribution, We have lots of companies on the left-hand side of the distribution with only few employees. And we have a few very large corporations, not so many, but a few with a lot of employees. In such cases, the arithmetic mean is higher than the median. In such cases, it might be appropriate, or it might be better for describing your data to use the median instead of the arithmetic mean. Just think of, you should explain to a foreigner who has no idea about the economy of the UK, the companies that are operating there. And you describe this by company size, so the number of employees. You use the arithmetic mean, but the arithmetic mean is dragged to the right, if you will, by these few large corporations. And then this foreigner comes to the UK, and virtually every company he enters, he is in contact with, has smaller employees or fewer employees than you told him with your arithmetic mean. In these cases, the median can make very much sense, or can make more sense for describing a data set. And of course, you do not only have right-skewed distributions, you might also have left-skewed distributions with a lot of elements with high values and only few with lower values. In these cases, the arithmetic mean, you can understand this is dragged to the left, the arithmetic mean is smaller than the median. Finally, the measures of dispersion. So these are the rather simple ones. You can look at the minimum value, the lowest value of your data set, the highest value of the data set, the maximum value, and you have quartiles, like Q1. That is the value that marks the lowest 25% of your data set. And Q3, that is the value above which you find the highest 25% of your data set. The range is maximum minus minimum, so in which range is your data, and the interquartile range is Q3 minus Q1. Let me show you this as an example. So let's assume this is the age. So our youngest participant is 10 years of age and our oldest is 40 years of age. So the minimum is 10 years and the maximum is 40 years. Now we have the first quarter, second, third, fourth quarter. So Q1 is at 14 years. Q3 is at 29 years. So we can say 25% of our participants are 14 years or younger, and 25% of our participants, 1/4, is older than 29 years. And then the range would be 14 minus 10 is 30, and the interquartile range is 29 minus 14 is 15. What I say, the more fun measures of dispersion are the variance and the standard deviation. And here, I suggest all hands on deck. Of course, if you understand the variance, you have understand a lot about the heart of statistics. The variance and therewith the standard deviation are not only important in descriptive statistics, they will also be important in inferential statistics, which I explain in the next lecture of this crash course. Of course, the variance, in some form or another, underlies most procedures, most analysis of inferential statistics, given the assumption that this analysis is based on the metric scale of measurement. All right, let me try to explain this again with a perhaps stupid analogy. Let's assume we have two countries, country A and B. In each of the two countries, you have only 2 inhabitants. And you are tasked to determine or describe these countries with regard to income. In country A, both inhabitants have an income of £50. In country B, one inhabitant has an income of £100 and the other inhabitant has an income of £0. If you now only use the arithmetic mean, you would say, all right, these countries are quite similar. Both have an arithmetic mean and average income of £50. But you're probably a bit off there, because a country in which all of the citizens have the same income, if that is too healthy, I don't know. That smells very much like socialism, and that wasn't too ideal, the outcome of that in mankind's history. The other country, country B, income of £100 and £0, is also not the healthiest of countries if one earns everything and the other earns nothing. Civil unrest and possibly a revolution are around the corner. So to bring this in a broader context, of course, countries do not only have 2 inhabitants. Let's take this country A and B example and use the distribution on the right-hand side. On the x-axis, you have the income, £0 to a few million pounds. The y-axis represents the frequency then. From our example, country A, both inhabitants have £50 income. Of course, we have more inhabitants. They would be something like this red distribution. All of the inhabitants have roughly the same. There are no super poor and no super rich people. They're roughly at the same income. It's a very homogeneous distribution. From our example, country B with more inhabitants would be the blue distribution. We have a few who are quite poor, and we also have a few who are really rich. It's a rather heterogeneous distribution. And for this, we need an indicator. The indicator, if our values are close to the arithmetic mean, or if our values are quite far from the arithmetic mean, is the standard deviation. The variance is sort of the step you need to do first, you need to calculate first to be able to come to the standard deviation. Here the definition, and I will explain both variance and standard deviation in more detail in a moment. The variance is the average squared difference of values from the arithmetic mean, whilst the standard deviation can be understood as the average difference of values from the arithmetic mean. Let me give you another example to explain the equation of the variance. And, as I said before, it is a good idea to understand this. You will get to the bottom or the secrets, the deepest secrets of statistics, and they will become easy. So let's assume we have 4 participants and we have measured on whatever scale and came up with participant 1 had a 6, 2 has a 2, 3 has a 6, and the 4th participant has a 2. The arithmetic mean in this case is 4. I think this is intuitively obvious, but you could also calculate 6 plus 2 plus 6 plus 2 divided by 4, that is 4. Here, with this simplified data set, we can say, all right, the values are either too higher, the measured values are either too higher or too lower than the arithmetic mean. But in a more complex data set, we cannot see this so easily, and there we need a coefficient indicator for this. Now, at first glance, to calculate the dispersion, we can say, all right, simply, we are doing xi, the measured value, minus the arithmetic mean. So xi minus x average, measured value minus arithmetic mean, and then we sum them all up. If we do this here, we have plus 2 plus minus 2 plus 2 plus minus 2. And that comes to 0. And whatever data you have, whatever numbers you have, this equation will always come to 0. Of course, the deviation above and below the arithmetic mean, they will equal each other out. So this does not work. But we have a trick in mathematics, and that is minus times minus equals plus. So we can get rid of the minus by squaring our values. So again, we take measured value xi minus arithmetic mean x average. and we square them. We multiply them with themselves. In our case, it is 2 times 2 is 4, minus 2 times minus 2, again, minus times minus equals plus, minus 2 times minus 2 is 4, 2 squared 4, and then minus 2 squared 4 again. So 4 plus 4 plus 4 plus 4 equals 16. And here we have the equation. This equation is the numerator of the variance. We had 4 participants. Then we divide our 16 by 4. So now we have the entire equation for the variance. 16 divided by 4 equals 4. Here we can see, wait a moment, our dispersion is not 4. The values are not 4 above and below our arithmetic mean, they're 2. The reason why we have inflated this dispersion is our math trick, with which we want to get rid of the minus, the squaring. Second the math trick comes into play. The antagonist of squaring is the root square. So we take the root square of the variance, and then we have the standard deviation. In our case, the root square of 4 is 2. And now we can see, happy days, that's actually true. Our values are either too higher or too lower than the arithmetic mean. So this is important for descriptive statistics, as in a research paper. Whenever you report an arithmetic mean, you also need to report the standard deviation. But as I said before, it is also a very good idea to understand the variance, as the variance, some form or another, underlies all of the inferential statistics that are working with metric variables. And even a step further, the variance as a measure of dispersion is very important in statistics. Of course, the dispersion, that is the word in statistics. If you look out of the window now, you see trees, cars, people, the sky, and so forth. That is your world you're in. In statistics, this world is the dispersion. The variance is a measure of this. This will come back with inferential statistics. So I hope I could give you a very good overview and understanding of descriptive statistics. The next time, it is the last lecture of this crash course. It is about inferential statistics. Until then, I wish you all the best, and it is bye-bye for now.